Okay, if I'm correct, I think we should start now. So, hello everyone. My name is Arnaud Legrand. I'm from University Grenoble Alps and CNRS in France, and I will be the chairman for the last but not least session of Europa, in particular the track Performance and Power Modeling, Prediction and Evaluation. So in this session, we'll have 5 articles. We have selected 5 papers in this track, which ends up providing us with a nice variety of topics. Indeed, in this session, we'll cover performance optimization under power constraints, failure modeling in supercomputers, optimization of the performance of big data applications, scalability of OpenMP implementations, and effectiveness of vector length instruction in modern processors. So I will give a brief presentation of every paper, mostly the name of the author and where it comes from in the title, and which should leave us with about 5 minutes for Q&A. So do not hesitate to ask your questions on the Slack channel. If there is no question from the audience, I will ask some questions based on what the reviewers asked and commented during the reviewing process. I will pass them on the Slack channel as when the YouTube presentation starts. Okay, so our first article is entitled Operation Aware Power Capping, and it's going to be presented by Wang from Harvard University in Germany. And so if we can start with this presentation, just do that.
My name is Wang. Today I want to give you a talk about operation-aware power capping. At first, what is the power capping? Why do we need power capping? As we know, current and future HPC clusters have a very high power draw. For example, the flagship cluster, the Fugaku cluster from Japan, has a peak power draw of over 28 megawatts. The higher power draw challenges the infrastructures in terms of power supply and cooling, especially if you want to cover the peak power. On the other hand, the peak power doesn't occur very frequently during normal cluster operations. If you can power cap the cluster, then you can save the investment to the infrastructure, even you can reuse the old infrastructures. However, power capping can cause computational performance degradation, especially if the power cap is lower than the actual power consumption of the cluster. In this case, the clock rate of the hardware needs to be reduced to meet the power cap. There are works looking at how to enforce a power cap, how to optimize the performance of power capped hardware. We did a similar investigation in this work, but in different ways. In this work, we want to mitigate the performance reduction of power capped hardware through individual power management for components. The agenda for today, at first, we will look at the power management of components. Then I will present some performance results on the system default power capping. Then I will introduce the power-aware power management, then evaluation, and at the end, a conclusion. This figure shows a very simple computing node. It consists of a processor and 2 accelerators, and to the processor is the DRAM attached. Each component of this node has its own power management tools or interface. If we look at the processor, especially the Intel processor, it can be divided into core area and uncore area. The cores doing calculations and perform operations. The uncore performs data operations like memory controller and last level cache. And besides, they also have the QPI and package control units. Both areas can be power managed separately. We employ DVFS, dynamic voltage and frequency scaling, to scale the frequency of core. And we employ the uncore frequency scaling, UFS, to set the uncore frequency. Besides, Intel provides another interface or technology for power management, the runtime average power limitation, for short RAPO. We can employ RAPO to measure the power draw and enforce a power cap. However, RAPO handles the processor as a unit, and it doesn't distinguish the power draw of cores and uncore area. In this work, we did measurement and evaluation implementation on Intel Xeon E5 processor, which has 12 cores, and the TDP of the processor amounts to 205 watts, and the hardware specific minimum power of this processor amounts to 53 watts. And we did the first measurement with a power cap to 53 watts, and we executed the BTCG-MG benchmark repeatedly. All three benchmarks are parallel benchmarks which uses 12 cores. Each time we set the core and uncore frequency differently, and we measure the execution time. Then what do we see in these figures? The top right of each benchmark are executed with the system default setting, namely the maximum core and the maximum uncore. And if we look at the computation time, work time of the execution, with the system default setting, the time is not the shortest. If we look at the optimal setting for this thing, with the optimal setting, the BT benchmarks, the execution time of BT benchmarks can be reduced by 1.7% compared to the system default, and similarly 1.2 and 7.4% for CG of the MG benchmark. On the other hand, we see the optimal setting, the optimal uncore and core setting for BT, CG, MG are quite different. That's because BT, and because these three benchmarks have distinct operations, like they have different CPI and memory bandwidth usage. From these figures, we can conclude that if we want to have optimal setting, we have to pay attention to the operations performed. That means we need to recognize the operations at first and then adjust the frequency accordingly. In this work, we focused on HPC workloads, and the HPC workloads usually performs operations in iterations. We assume the operations among iterations are quite similar. In this way, we can recognize the operations in the previous iteration and adjust the hardware in the later iterations. So it's very crucial to understand or to recognize the operation performance. Basically, we differ some memory and compute intensive operations. We recognize such operations based on the hardware performance counters. These counters can count thousands, more than thousands different events. The question is which event should we use for our operation recognition? We made the selection based on the top-down performance analysis. So in general, if you look at a processor, it can be separated into front end and back end. The front end fetches and decodes the instructions and receives the instructions in some space, and the back end schedules the instructions to execution unit. The front end executes in order, the back end executes in out of order. So then we can a processor can be during operations the processor can in one of the four states. The stored state and unstored state. If a processor is stored, no instructions will be performed at some time point, and the store can be caused by because no instructions can be performed because they all have cache misses. Can also be stored by other reasons, and if the processor is unstored, then the processor is performing some instructions, but still other instructions can have data misses because the backend is executed out of order. It can also happen in the ideal case that all instructions does not have cache miss. If we look at the period of execution with T, and it can consist of the time with stores and the time without stores or unstored. And if we compare the time stores with cache misses and stores unstored without cache misses, we define the operations as a memory intensive is this value is higher than this value. In this case, it's better to reduce the call frequency and increase the uncore frequency. Otherwise, we should increase the call frequency, reduce the uncore frequency. So, with our strategy, we did measurement. At first, we executed the BT benchmark again and set the power cap to 53 watts. At the runtime, we sampled the core and uncore frequency. At the beginning of the execution, the core and uncore frequency are quite similar, or all the same. After some point, our strategy started to set a different frequency from time to time. After couples of iterations, and our method, our algorithms noticed that the executions entered a stable state. That means the optimal setting have been figured out, so no other data collection is necessary. So the frequency pattern repeated again and again. At the end, we evaluated our OEPM with two real applications, the SVIM and the BVIM application. For the measurement, we set different power caps and we measure the execution time with default system setting and OEPM. We see here with the low power cap, the OEPM can improve the execution time by 6.3%, and for BVIM, the execution time can be reduced by 4.6%. And that means the OEPM can bring some benefit for the execution time. So, to the conclusion, as we see, if the hardware is a power capped, the system default hardware setting causes some performance loss more than necessary. We do some optimization based on the performed operation. We distinguish the operations between memory and compute bound. We employ the DVFS and UFS to adjust the power consumption of different components, and we can achieve 6.3% performance improvements compared to system default setting. That's all from my side, and thank you for your attention.
Hello.
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 So, oh, it's very noisy now. Okay, so we have a first question on the Slack channel. I'm going to rephrase it. I'll just say it. Could you give us some insight as how you categorize work as compute intensive or memory intensive, and more precisely, which metrics and how are they compared and used?
So, for the compute intensive and memory intensive, there is no clear definition. So we just, should I share the screen? Can I share the screen?
Just give it a try.
Yes. Do you see that screen?
Yeah.
This is a slide I used for the talk. How do we recognize the memory bound and the compute bound operations? We use the top-down performance analysis model, which was introduced by Intel. We employ the hardware performance counters to identify the operations. As you know, there are thousands of hardware events which you can measure. We select the 4 metrics for the operation pattern recognition, and that means we can measure how long time is the operation stored or executed due to memory, due to cache misses or without cache misses. And then we just simply compare the 2 values, the time with stores and the time without stores, and the time with cache misses and the time without cache misses. Then we recognize the operations. Does that answer your question?
It's answering in Slack. Okay, there's another question related to one of the other questions I raised. You assume that your code is regular and stable through time, something like that. And so something related is, did you try your technique with distributed code?
Basically, you can use it for distributed code. Of course, for the implementation, it's a little bit complicated. Yeah, that's all.
Have you given it a try yet, or is it just something that you think is possible?
We tried in another work, but with different algorithms. Because for the implementation, for example, in this work, we're using the OpenPT interface. In other works, we use the PNPI interface, which is basically the same as OpenPT. In the theory, I don't see anything which can make this difficult to try these algorithms.
Okay.
Yeah.
Philippe, any comment on the answer?
So maybe I should go through the other questions from the reviewers.
Yeah, we can go with one of the last one. One of the reviewers noted that the solution has been evaluated on a single cluster with CPUs from one hardware vendor for the moment. Have you experienced your technique with other machines as well? In particular, in your introduction, you mentioned Fugaku, which is made of ARM processors, if I'm correct. And I don't know if it's possible to play with uncore frequency on such processors.
So, yes, this is a limitation from our work. We only focus on the Intel CPUs because we don't have access to AMD CPU or something like that. In the last few days, I also look at the GPU. As described from the NVIDIA tools, it should be possible to adjust the core frequency, but there the uncore frequency or the memory frequency is most likely fixed. But the effect is more or less the same. It's just lets the adjustment of the uncore area away. You adjust the core frequency only, but the effect should be similarly, and the improvement may be a little bit less, but you can still see some improvement. We will go to we will look at the GPU implementation in the next step, but most likely we will not using the profiling tools, like we will not using the OpenPT. That also means we don't want to assume that the operations among iterations are the same, which was asked by the previous questions.
Okay, thanks a lot. There are other questions and comments on the Slack channel, but I'm gonna have to try to keep the timing okay, otherwise people will be mad at me. So we'll stop there for the questions, but do not hesitate to just comment and answer some of the other questions or the ones that could pop up on the Slack channel. Thanks again.
Thank you.
Let's move to the second talk, which is entitled Towards a Model to Estimate the Reliability of Large-Scale Hybrid Supercomputers. So the talk will be given by Elvis Rose from University of Costa Rica in San Jose.
Hello everyone, my name is Elvis Rojas. I am going to talk about the paper called Towards a Model to Estimate the Reliability of Large-Scale Hybrid Supercomputers. This work was carried out together with researchers from Oak Ridge National Laboratory. The figures show us the top 20 supercomputers from the last 15 years. The figure shows that the number of processor sockets has stagnated, but accelerators and memory per socket continue to increase. To maintain the required growth in computing power, hardware engineers have employed complex and heterogeneous designs. Modern supercomputers assemble an immense amount of processor, accelerators, memory modules, and more parts. The consequence is a high failure rate. As technology becomes more complex to provide high scalability, reliability becomes more difficult. Therefore, it is crucial to describe failure types along with their frequency and impact. For that reason, this paper provides a reliability model for supercomputers based on failure characterization of hardware components. Contributions. The contributions of this paper are as follows. A collection of insights of 5-year failure record, Titan supercomputer. One of these findings include the trends or epochs in the failure data, automatically detected by an algorithm. A whole system failure model using mixed Weibull distributions. Our model outperforms the traditional Weibull distribution and allows the representation of different configurations according to the prominence of a component in the machine, processor, accelerator, memory. Failure rate predictions for different hypothetical exascale machine configurations. Such projections are correlated with power consumption of each configuration to understand the trade-off between performance and energy. Outline. The outline for this presentation is as follows. First, I am going to talk about the analysis that was performed with the failure data of Titan supercomputer. I am going to talk about the methodology used to filter and to analyze the failure data and the key elements found with the failure data analysis. After this, I will present the proposed reliability model and some projections on supercomputer configuration that we made based on the proposed model. Finally, I will conclude the presentation with some remarks of the work that was presented. System description. In this work, we use failure data from Titan supercomputer. Titan was a crazy system with more than 17 petaflops of performance from more than 18,000 nodes. Failure dataset. In this work, we analyzed 5 years of failure events on Titan from 2014 to 2018. In this 5-year span, the total number of events in the failure database was more than 2 million. After a filter stage, the number of events in the failure database was dramatically reduced by more than 99%. This massive reduction in the event is due to the presence of multiple redundant messages and warnings for the same failure. The figure failure propagation shows these redundancies as the cause-effect dependency of events. These are potential dependencies because in some cases an event can occur in isolation without the occurrence of the preceding event in the graph. Methodology. This figure summarizes the stage of the methodology. The methodology is composed of several stages. However, the most important are those related to data filtering, failure analysis, and reliability analysis. Failure filtering takes the preprocessed data and performs a series of tasks to filter redundant data and non-significant events. The failure analysis stage uses the filtered data and performs a series of analyses to model the behavior of failure events in the system. And the reliability analysis stage is used to describe the background of the statistical model that was used in this study. We implemented the mixed Weibull distribution to analyze the real and synthetic failure data. Findings. The main findings that we obtained after analyzing the failure data are the following. Most system failures in Titan are processor, accelerator, or memory related. Table 1 shows the failure distribution of hardware components according to failure classification. The failures related to processor, accelerator, and memory represents 92.45% of all failures. GPU failures are dominant, particularly those associated to GPU memory. Table 1 showed that 80.87% of all failures are related to GPU. The time series of GPU failures can be divided into 4 distinctive epochs. The figure below shows the result of using an algorithm to extract trends on the failure time series of 3 hardware components. Hardware component failures are statistically independent. We tested the possible dependence between failures of different hardware components. Time between failures of processor, GPU, and memory components follows a Weibull distribution. The figure below shows the CDF of the three components, and we see that the Weibull distribution fits better the MTBF data than log normal and exponential distributions. Analytical model. The theory of reliability provides a rich framework to study, analyze, and model failure data from supercomputers. The reliability function is the most frequently used function to perform live data analysis. It provides a probability of a component functioning with no failure for an amount of time. It is a function of time and a flexible way to derive the MTBF of a system. A key element to build a precise reliability function for a system is to find an appropriate distribution function for a live data analysis. We concentrate on finding a function that best fits the data and provides a precise reliability function for the system. The literature shows that Weibull distribution is a good fit for supercomputer reliability data and time between failures. The Weibull probability distribution is shown in this function, where alpha is the shape parameter and beta is the scale parameter. Although a Weibull distribution may adequately capture the failure data for all components in a supercomputer, it may fall short for modeling scenarios where the behavior of the component differs from one another. For example, where several components show different failure profiles, we may resort to a refined probability function called mixed Weibull or mixture Weibull function, and defined as in equation 1. Equation 1 models a system where failures come from different independent families, and it becomes an appropriate framework to represent failures of components in a supercomputer. We propose using a mixed Weibull distribution function to model the failures in a supercomputer. The figure shows a comparison of a single Weibull function versus a mixed Weibull function in fitting the failure data from epoch 1 of all components of Titan. Figure 8 presents how well the two alternatives fit the failure data using the KS test. The mixed Weibull model performed better than the single Weibull function, which can be seen in the probability plot of figure B. Extreme scale projections. We use equation 2 to estimate MTBF values of exascale system and contrast those values with their corresponding power consumption. We develop different supercomputer configurations taking into account three components: processor, accelerator, and memory. The proportion of these components was varied to reach exascale performance. Assumptions. The previous model analysis of this paper was made with failure data of Titan supercomputer. The failure data was generated from an AMD Opteron CPU, an NVIDIA Tesla K20 GPU, and 32 GB of memory. Nevertheless, to make realistic projections, we updated the CPU and GPU components to the actual time. We used the specification of the AMD EPYC 7742 and the NVIDIA B100 that have 2.3 teraflops of performance, 225 watts TDP, and 7.8 teraflops of performance, and 250 watts TDP respectively. Regarding memory, we only multiply the amount of memory RAM by a factor depending on the projection. To project the power consumption of an exascale machine, we consider the power draw of processor and accelerators. These components and the memory determine the maximum power required by a subsystem. Size and failure data. All the projections were made based on the data of epoch 1. This epoch was the result of the execution of 18,688 nodes with a proportion of 1:1:1, 1 GPU, 1 CPU, and 32 gigabytes of RAM. For that reason, if we wanted to model a different component proportion, we needed to generate synthetic data. The synthetic data was randomly generated for each component, but based on the wavelet shape and scale of the real data to ensure the same failure behavior. Projections. We developed a series of exascale supercomputer projections, varying the component proportions. Table 3 shows part of the experiments. The experiment shows the change of the GPU proportion. We see that when increasing the number of GPU, the MTBF decreased. This is a normal behavior considering that we were increasing the component with the highest failure rate. T10 supercomputer in Epoch 1 had an MTBF of 42.3 hours with the proportion 1:1:1, and the same proportion of an exascale machine has 9.98 hours. Nevertheless, Titan only had 0.027 exaflop relative to the projected exascale machine. Regarding the power consumption, we see that the simplest proportion, 1:1:1, has the highest power consumption because to reach exascale performance, it is necessary to use 99,010 sockets. Finally, it is important to remark that each proportion corresponds to a real supercomputers, Titan 1:1:1, ABCI 2:1:1, Summit 3:1:1, and Legrand 4:1:1. As a result of the projection, we can conclude that hybrid supercomputers are a good solution to reach exascale performance. Hybrid supercomputers need less hardware, and the power consumption is remarkably less than supercomputers without GPUs. Nevertheless, it is necessary to take into consideration that its system reliability could be affected by the increase in the GPU proportion. Final remarks. This paper presented the mixed wavelet distribution function as a more appropriate model for failure characterization and prediction in hybrid exascale supercomputers, starting from a collection of insights of a 5-year failure record of a leadership class supercomputer. We built a whole system failure model using mixed wavelet distributions. This model allows the failure prediction of different configurations according to the prominence of a component in the machine, processor, accelerator, or memory. Thank you for your time.
Okay, Elvis, are you there?
Hello, I am here.
Hello, Elvis.
Hello.
Thanks for the talk. Okay, so I'm going to start with the questions because I don't see any reaction at the moment on the Slack channel, and I'm going to start with with just a comment on the importance of reproducibility and transparency of our research. So I've seen that according to our recommendations, you've made the analysis scripts available on GitHub, which is great. But I was curious about the original data on which you've been working. Is this data available for others to inspect and possibly build upon it?
Oh, hello everyone. Unfortunately, that data is not available. Yeah, we access to the data through the researchers from the Oak Ridge National Laboratory, but in this moment the data is not available. Yeah.
Is this a legal reason or just a technical one?
In this moment, I don't know what is the reason, but maybe it's a technical reason. Yeah.
Okay. In any case, I would strongly encourage people to look in that. I would strongly encourage you to try to make it available because it's far more interesting for others that may want to, make something different out of this.
Yeah.
Okay, so some of the reviewers made comments about the fact that you mostly studied the epoch 1, whereas there were several epochs, as you explaining. Is there a reason for that, or does it make sense to study the other epochs as well?
Yeah, we divide the total time from 2014 to 2018 because the failure data are different across the time. We found that at the middle of the timeline there are an increase of GPU failures, and the reason was because there was a GPU malfunction. There was like more than 8,000 GPU that failed, and there is a known cause. Then we want to evaluate the real failure by the components. Yeah, and then we decide to use only the epoch 1 because that epoch was with normal, I don't know how to say, a normal failure, not generated by the GPU malfunction. Yeah.
Okay, thanks. But just to maybe to insist a bit, when you're in this abnormal situation, does the viable modeling assumption still hold or not? Or did you look into that?
Yeah, it's because the system administrator said that there is a assembling malfunction of the GPU. There is a known problem. There is not a problem for the use or problem for the pass of time. It's a malfunction problem of the assembling when the supercomputer was built. Yeah.
Okay, thanks.
Mm-hmm.
There's a question by Valentin Lefebvre regarding whether you measure the difference between your predictions using variable laws compared to using classical exponential distributions, and whether it's significant.
Let me see. Let me read the question.
Although I'm not sure what Valentin means.
Okay.
How the difference could be measured, except by measuring different distributions.
Okay. Yeah, we previously analyzed the data with 3 different distributions. We analyzed the data with Weibull, log normal, and an exponential distribution. The exponential distribution is the distribution that worst fits the data. Yeah, and the Weibull distribution is the better, that best fit the data. For that reason, we implemented and we modeled the reliability with a mixture Weibull distribution because it's an improve of the normal Weibull distribution. Yeah, but the exponential distribution is the worst to fit the data to do. Yeah.
Yeah. There's a question from Matthias explaining that he's not familiar with the field, but is curious about possible application of this work to, for example, provide services with a certain service level agreement, and whether there's successful implementations.
Okay. Wait a minute, I'm reading the question. No, I don't know regarding that. It's about the service level agreement.
Okay.
There is no successful implementation. I don't know about that. Yeah.
Maybe along this line, that there are many works that are tuning. When you're running parallel application at this scale, you want to make sure the failure don't ruin your application, so you checkpoint on a regular basis. And so how to optimize the optimal checkpoint interval has received a lot of attention. I'm not an expert either, but do you think that the work you've been doing with this mixture of variable distributions impacts this kind of work or not? Do you think they still apply, or it's often that they assume that they have failures come from availability distribution or things like that. So when you have mixtures, does it change anything, or is it or not?
About the checkpointing?
Yes.
We didn't analyze that the checkpoint part of the application. Maybe in the future we can study that part. Yeah.
Okay, maybe I just have one last quick question. So as you coming back to this question about epochs, you know, that's something changed at some point. There were some malfunctions. Do you see ways of detecting these kind of situations? Because somehow as you're saying, there is a normal regime where your system is behaving as a mixture of clean variable distribution, and something changes all of a sudden. So is it something that you think can be detected online or not, or maybe something you did not consider yet?
About the epochs where the epoch with the high failure rate, the GPU failure rate, was detected by the system administrator, because they see the increasing of failure on GPU. But our way to extract the epochs was with an algorithm to extract the patterns in the data. Yeah, I don't know if I understood the question.
So you did with information. You did it a posteriori, you know, as a post-mortem analysis with information from system administrators.
Mm-hmm.
My question is how easy this would be to do it online, because all of a sudden your inter failure rate is not anymore variable at all, because the parameters change. So maybe you can detect that. But okay, but probably this deserves a lot more study.
Yeah. Online is I think it's a difficult thing. Yeah.
Okay. Well, thanks a lot, Elvis, for your presentation.
Okay.
Let's move to so if there are other questions, again, do not hesitate to ask them on the channel, and Elvis, I'm sure, will be happy to answer them.
Sure.
Thanks again. Let's move to the third presentation, which is entitled, oh, wait, sorry. Whoops. Yeah, sorry. Let's move to the third presentation, which is entitled Learning-Based Approach for Evaluating the Capacity of Data Processing Pipelines. So this presentation will be given by Matthias from University of Grenoble. And so let's go.
Hello everyone, I am Matthias, and today I will present my paper entitled A Learning-Based Approach for Evaluating the Capacity of Data Processing Pipelines. This work was done at University Grenoble in collaboration with Noel de Palma. In this paper, we study data processing pipelines, and we consider a pipeline comprising Apache Kafka, Spark Streaming, and Cassandra. Typically, in this pipeline, clients send messages to a publish-subscribe messaging system, which is in our case Kafka, a big data processing engine and analysis framework. Spark Streaming integrates with Kafka to consume these messages, apply some operations in these messages, and send the result to NoSQL database management system Cassandra. This software stack is widely used in production for analyzing streams of data. Furthermore, this kind of stack is complex, and in general, it's difficult to know when the system has reached its maximum capacity in terms of a throughput. And by throughput, we refer to the number of requests the system can handle per time unit. This is an important matter as it impacts our decisions for resource provisioning. Furthermore, deploying a system with different setups leads to different performance. These setups might vary based on different factors, for example, the number of Kafka partitions, the compression algorithm, the number of Spark executor, the replication degree for both Cassandra and Kafka cluster, etc. As we can see in the figure on the right, where we show the system throughput as a function of number of clients, we observe that the maximum throughput that the system can achieve for the 3 different setups is different. Also, the number of clients to achieve this throughput is different. The key challenge with such complex system is to know whether the system has reached its maximum capacity in terms of a throughput or not. And to answer this question, metrics at both hardware level and software levels can be used to evaluate the state of the system. The crux of the problem here is that each component in the system exports a large number of metrics, in order of 10 to 100 metrics per component, and trying to make sense out of these metrics is an arduous task. Thus, in this paper, we present the following contributions. We build a tool based on machine learning techniques to automatically determine the state of the data processing pipeline. This tool analyzes non-intrusive metrics at both hardware and software levels. Our evaluation analyzing more than 70 metrics shows that the obtained models can achieve up to 88% of prediction accuracy, and these models are robust to significant change in the configuration setups. In this context, there has been many works that use machine learning techniques to identify performance issues in multi-tier distributed systems. Most existing works consider a single type of metrics. We will show in our evaluation that models based on a single type of metrics, for example, resource consumption or waiting time, achieve low prediction accuracy. Other kind of works focus on different objectives, for example, satisfying predefined service level objective, which is a different problem from ours. The work done by Arnaud shares the same objective as us for web stacks. However, the author assumed that the workload is known in advance. We believe that this kind of information might be difficult to obtain in practice. We describe our approach as following. We use classification algorithms to determine the state of the system based on the values of metrics. We compare the result obtained when providing different selections of metrics to the prediction models, and we test the capacity of the obtained models to generalize to different cases. We consider different configuration setups, 15 setups for the Kafka cluster and 10 setups for the full data processing pipeline. These setups vary based on different factors, for example, the message size, the number of partitions, etc., as we can see in the table on the right. We also consider different workload applications. These applications vary in their characteristic between a simple word count application where the frequency of each word is counted, to Twitter sentiment analysis that monitors people's opinions on different topics, to a machine learning based application that predicts delays in airline flights. Regarding the studied metrics, we use high-level abstraction classification to categorize the studied metrics, as we can see in the table on the right. For example, the idle thread type represents the average number of threads that they are in idle state, as they are waiting for incoming requests from the clients or they are waiting for a reply from other threads. As we can see in the pie chart on the left, that the studied metrics cover all the types we've just listed in the table. To better understand what kind of metrics should be used as input to build models that achieve good prediction accuracy, we test several selections of metrics. The first selection is the all selection, which includes all metrics exported during our evaluation on both hardware and software level. The software level selection includes only software level metrics. This implies that resource consumption metrics are excluded from this selection. The hardware level response time and waiting time selections, they include a single type of metrics that correspond to their types, and this kind of selection are representative of kind of metrics are studied in some related work. The last selection of metrics is what we call recommended selection, and this selection includes only metrics that we identify by our manual analysis. More precisely, it includes metrics that change their behavior significantly when the system changes its status from not saturated to be saturated. We evaluate the models with 5 different classifiers, including decision tree, random forest, support vector machines, logistic regression, and gradient boosting tree. We use different classifiers to ensure that our conclusions are not simply due to a bad choice of a classifier. Also, we use these classifiers as black boxes without tuning their hyperparameters, as our goal is to demonstrate the feasibility of our approach and not to find the optimal classifier. Other machine learning techniques like neural networks and deep learning are excluded due to the limited number of samples. We use binary classification to label our data points into 2 classes: the not saturated class, where adding more clients would improve the system throughput, and the saturated class, where the system has reached its maximum capacity. We test the capacity of the obtained models to generalize to new setups, where the deployment configuration might change by tuning some software settings, for example, changing the number of Kafka partitions. Also, we test the capacity of the model to generalize to new number of clients, where the deployment configuration of the system is decided early, but the load injected might change while the system is running. We also test the capacity of the model to generalize to both new setups and a new number of clients. And finally, we test the capacity of the obtained models to generalize to new workloads. In this presentation, we'll present the results for the first and the third case. For the other cases, detailed results are presented in the paper. To train and test models, we use the leave P out cross-validation schema, considering P equals to 2. The training and the testing process are executed 5 times, and we compute the average accuracy over these 5 runs. We consider as a baseline always predicting the majority class, which is the not saturated class for the full data processing pipeline. We present the result for the full data processing pipeline. However, detailed results for the Kafka cluster use case are presented in the paper. First, we present the result when generalizing to new setups. We test the capacity of the obtained models, as we can see in the graph on the right, where the x-axis represents the different selections of metrics, and for each selection of metrics, the different colors represent the different classifiers. The horizontal dashed line represents the baseline, which is in this case the not saturated class. We can see that most models achieve better accuracy than the baseline. However, most models based on recommended metrics, which appear to be the second column, achieve better accuracy compared with models based on a single type of metrics, as we can see for hardware response time and waiting time selection. Furthermore, models based on hardware metrics, as we can see, it appears to be the fourth column in the graph, achieve low accuracy. We also test the capacity of the obtained models to generalize to new number of clients and new setups. We can see that models based on a single type of metrics, including hardware response time and waiting time selection, achieve an accuracy lower than the baseline. Still, the best results are achieved with model based on recommended metrics, up to 75% of accuracy using the GPT classifier. To better understand the obtained result, we analyze the prediction errors for models based on recommended metrics when it comes to generalize to new number of clients with the new setups, as we can see in the graph on the right, where the x-axis represents the different selections, the different classifiers. For each classifier, the blue area represents the percentage of correct prediction. The red area represents the percentage of errors that model make when when they predict that the system is saturated while it's not saturated, and this corresponds to the false positive. The green area represents the percentage of errors that model make when they predict that the system is not saturated while it is saturated, and this corresponds to false negative. For the last part of the error, which we call it the gray error, here we define a gray area that corresponds to points where it's difficult to determine if the system is saturated or not. For this area, the models predict that the system is not saturated, while our labeling says it is saturated, but we consider that these errors are minor. Furthermore, these errors vary between 30% and 45% of the total error. To conclude, in this paper, we evaluate the capacity of data processing pipeline. We build a tool based on machine learning techniques to automatically predict the state of the data processing pipeline. This tool is based on non-intrusive methods at both hardware and software levels. We apply our approach to a single tier, two-tier, and full data processing pipeline. We also evaluate the models based on different selections of metrics and using different classifiers. Our main results show that very accurate results are achieved, up to 88% of prediction accuracy. More precisely, models based on a combination of metrics of different types can achieve best accuracy. Furthermore, we also show that models are robust to changes in different configuration setup. That's all, and thank you very much for your attention.
Hi, my name is Tim Yama.
Okay. Well, thanks a lot, Maha, for your presentation.
Thank you very much, Arnaud.
As usual, feel free to ask questions on the Slack channel. In the meantime, I will ask with a few of my backup questions. So first of all, thanks for taking into account the comments from the reviewers, since you answered already one of them regarding the amount of false positive, false negative questions. Well, not questions, but classifications. There is one for which I'm not sure you really answered it, which was related to the need to exclude some misleading metrics to get accurate results. Can you elaborate on this one?
Yeah, actually, the question was, can this process be automated or not? So to be clear, first of all, what those misleading metrics, what they mean. So actually, we've done in my thesis, I cited actually my thesis in the paper. So we've done analysis, and it's not fully automated. So where we study the evolution of metrics values and try to correlate this evolution with the system throughput. And based on that, we came up with 4 categories of metrics. So the misleading one, and those one actually they impact the accuracy of the obtained models. So these metrics actually they look reliable, which means that they have significant change in their behavior. However, this change doesn't occur at the moment where the system changes its status from not saturated to be saturated. So this process actually it's not fully automated. It can be automated. Actually, I have investigated, and there are plenty of research topics in this area to know how you can detect inflection points in matrix graphs. So yeah, it can be done, yes, but we didn't do it yet.
Okay, sure. No, detecting breakpoints in behavior change is definitely difficult. There was one other question related to the size of the learning set, the time it takes to do such kind of processing and such learning. Maybe you can comment a bit on that.
So we explained that the data set size, we give it as a formula. So it's the number of setups multiplied by the number of runs, multiplied by the duration of each run, multiplied by the number of metrics, which makes it an order of 65,000 rows. Regarding the duration, so each experiment was run for 15 minutes, excluding the warming up and the cool down phases.
Okay. Matthias is asking a question, so which I will read now. I assume that the prediction is calculated online. If yes, then does the length of the predicted period allow to react to changing conditions? And I assume that it is the main goal to avoid data overflow.
Yes, so the prediction is calculated online. Actually, the duration of building the models is not, it doesn't take much, so it's an order of few minutes. This is the main goal to avoid data overflow. Actually, to avoid that data overflow, if I understood this expression correctly, we used the leave out schema, leave p out schema to avoid what we call overfitting, which means that you don't want really to get a very good prediction result because of a lucky selection of the test set. So what we have done in this schema, as I mentioned in the slide, and it's more detailed in the paper, we assume that p equals to 2, which means p here refers, for example, to the number of setups. So we take it equals to 2, which means that from all the observations, we remove all the setups. If we want to test for setup number 1, we remove from the training set the setup 1 and another setup randomly, and we keep repeating that to ensure that all those p observation as being considered as test set. So this to avoid overfitting, if I understand correctly the question.
Okay, it looks, sorry, I was muted, I didn't realize. Okay, I'm gonna reproduce my reproducibility question one more time. Did you have the time to make all the data, code, and everything available for others to reuse? I know how that's a lot of work when you do it afterward, but is it something you've been able to do?
So the data, I mean, we try to make it available, but it's administrative legal rights thing, but I'm working on that. Yeah, I would like actually to put the data to make it available, also the code, but after I clean the code for sure. But yeah, I would like, I'm not promising, but I will try, yes, to make it available.
My opinion on that is that unclean or dirty available code is better than unavailable clean code, if I may. Okay, thanks a lot, Maha.
Thank you very much, Arnaud.
You're welcome. If we don't have any other question, let's thank our speakers again, and let's make our break now. We'll come back in like 20 minutes, if I'm correct, for the next two papers. Stay tuned. As I would say, the next two papers are going to be about a comparison of the scalability of OpenMP implementations by Tim Yammer from TU Darmstadt, and the second one will be on the effectiveness of vector length agnostic instruction set by Andrei Poinaru from University of Bristol. So see you soon. And if you have other questions, do not hesitate to ask them on the Slack channel. I'm sure the authors will be happy to discuss about all that. See you soon.